Hi dears, in this video we are going to discuss about electrostatic potential energy due to collection of charges. Okay, right. In the previous video already we have discussed about if 2 point charges are there, what is the amount of electrostatic potential energy we have discussed. Now in this video we are considering there are 3 point charge system. If 3 point charges are located in different places, what is the total amount of electric potential energy or electrostatic potential energy? Okay, for that we have to know what is the amount of electric potential at a point due to a point charge. Okay, it is already we have discussed. Now first we can write what is the amount of electric potential at a point due to a point charge Q. Let us consider Q1 is the charge, it is located in some places. Okay, from that point charge at a distance of r, what is the amount of electric potential? We know that electric potential due to a point charge is given by V is equal to 1 by 4 pi epsilon naught into Q by R. Since we are taking Q1 is the point charge, we are representing here Q1 by R. Okay, now this is the amount of potential energy. Okay, now what is the definition for electric potential? Electric potential, it is defined as the amount of work done to bring the unit positive charge. So what is the unit positive charge? We are considering Q1. So to bring the unit positive charge Q1 from infinity to the particular point, what is the amount of work done? That is known as electric potential, right? Suppose if we consider another point charge is also there. Suppose we are assuming that Q1 is the point charge here. At a distance of r, it will produce some amount of potential. It may be considered as V1. Now we are assuming another point charge, that is nothing but Q2. Now we are assume that this point charge Q2 is also going to be assembled. Okay, or it is brought from infinity to the particular point. Now what is the amount of work done? Here external work must be done because it has to overcome the electric potential produced by the charge Q1, because the charge Q1 it will produce some amount of electric potential. Then one more thing we have to remember, that if Q1 is the charge, it should produce the electric field radially outwards. In all the directions it will produce a electric field. Now if we consider the point charge Q2, it is also Q positive, then due to the same kind of charge they will repel each other, so that external amount of work has to be done to overcome the repulsive force. Okay, right. So in this case we are assuming that another point charge Q2 is brought from infinity to that point at a distance of r from the Q1. Then what is the amount of work done? Amount of work done, it must be equal to the product of the charge and the electric potential produced at that point. Which charge? The charge which is going to be brought. What we are going to bring? Q2. And product of electric potential means already the electric potential is being produced by the charge Q1. So that it is given by W is equal to Q2 into V. So this is the amount of work done. Okay, this amount of work done, it will be stored as the potential energy. Okay, from the 11th standard we have studied potential energy is nothing but amount of work done. Okay, so that this equation can be rearranged as W is equal to U is equal to Q2 into V. So what is V? V is nothing but what? The potential produced by the charge Q1. That is nothing but 1 by 4 pi epsilon naught into q1 by r into q2, so that it is simplified as 1 by 4 pi epsilon naught q1 q2 by r. So instead of we are substituting the value of electric potential produced by the charge q1. Okay, so that the electric potential energy is given by 1 by 4 pi epsilon naught into q1 q2 by r if 2 point charges are considered. Okay, right. Then if the electric potential energy is given by the formula 1 by 4 by epsilon naught into q1 into q2 by r, what are the factors deciding? It can be asked in the 1 mark question. Here we can understand that 1 by 4 pi epsilon naught is common. Its value is given by 9 into 10 to the power 9 Newton meter square coulomb power minus 2. Okay, then what is q1 q2? They are unit positive charges, so charges will not be changed, so we cannot consider these two. Then what will be the remaining is nothing but the distance. So the electrostatic potential energy depends on the distance between the 2 point charges. Okay, so 1 by 4 by epsilon naught is common constant, q1 constant, q2 constant, so remaining is given by u is inversely proportional to r. Okay, so that I have given in this sentence the electric potential energy only depends on the distance between the 2 point charges. Okay, then the amount of electrostatic potential energy will be remains the same if we assume the charge q1 is fixed and q2 is brought from infinity. Because you can ask one question, sir, in the first case we are assuming q1 is fixed, q2 is brought. Suppose if q2 is fixed, q1 is, which is at a distance of r from q2, if we are bringing the charge q1 to q2, what is the amount of work done? The same amount of work will be done, because either q1 or q2 is moved. That means any one of the charge remains kept constant, remaining charge is moving. So that if we are moving the charge q1 and q2 is fixed, or q2 is moving, q1 is fixed, whatever it may be, the amount of electrostatic potential energy will be remains the same. Okay, that is given here. If we assume q1 is fixed, q2 is brought, or q1 is brought, q2 is fixed, so only the amount of electrostatic potential energy depends on distance between the 2 point charges. Okay, right. Then next, if 3 point charges are there, then what is the total amount of work done? If 3 point charges are there means, we can imagine this diagram. At a point A, q1 is there. At a point C, I have taken. Okay, no problem. That is q2. At a point B, q3 is there. So distance between the charge q1, q2, r12. Okay, distance between the charge q1 and q3, r13. Between the charge q2 and q3, r23. Now, what is the total electrostatic potential energy? Okay, right. To find out the total electrostatic potential energy, we have to bring all the charges one by one. For example, if q1 is fixed means q2 has to be brought from infinity to that point. Then one more thing, if q2 is brought from infinity to that point, some amount of work has to be done against the potential produced by the charge q1. Right. If we consider the third charge, okay, if third charge is going to be brought from infinity to that point, the work done should be against the potential produced by the charge q1 and also against the potential produced by the charge q2. Okay, so the amount of work done to bring the third positive charge or third unit positive charge, the amount of work has to be done more, because it has to overcome the repulsive force or against the electrostatic force produced by the 2 point charges. Okay, Right. If we consider only the charge Q1, less amount of work done. Otherwise, we can say that no work done is needed because there is no other point charges are there to produce the repulsive force, or they cannot produce the electric field because there is no other charges. So that to bring the unit positive charge Q1, no work done is needed. To bring the unit positive charge Q2, some amount of work has to be done to overcome the repulsive force of Q1. To bring the third unit positive charge, we have to do more amount of work to overcome the electrostatic force between the charge Q1 and the Q2. Okay, now we can see one by one. So in the first point, what I have given, bringing the charge Q1 from infinity to that point, no work requires because there is no other charges already present in the vicinity of the Q1. That means there is no other point charge before the charge Q1. Okay, so no work done is needed, no repulsive force will be there, no field will be there, no potential will be there, because this is the first charge we are going to bring from infinity to that point. Right. Now, if we consider the another point charge Q2 from infinity to that point B, the work must be done against the electric field exerted by the charge Q1, because if Q1 is already there means it will produce some amount of electric field radially outwards. Okay, if we consider Q1 is there, the electric field is acting outwards in all the directions. If we bring the charge Q2 from this direction or this direction or this direction, whatever it may be, the amount of work must be done which is greater than that of the electrostatic force of repulsion. Okay, so that to bring the charge Q2, some amount of work has to be done against the electric field created by the charge Q2. Okay, what is the amount of work done? It will be given by Q2 into V. Here there are 3 point charges are there, so we represent V1B. What is meant by V1B? It is amount of potential, electrostatic potential produced at the point B due to the charge Q1. So 1 represents the charge, B represents at which point. So that this equation can be written as U is equal to 1 by 4 by epsilon naught into Q1 Q2 by R12. What is meant by R12? It is the distance between the charge Q1 and Q2. Okay, right. Then one more thing we have to remember, that the expression is same when Q2 is brought from infinity to that point. That means Q2 is fixed, Q1 is brought, or Q1 is fixed, Q2 is brought. Whatever it may be, already we have discussed earlier. What we have discussed? The electrostatic potential energy has the same magnitude if Q1 is fixed, Q2 is moved, or Q2 is fixed, Q1 is moved. Only it depends upon the distance between the 2 point charges. Okay, again I have given this point. Then we are going to bring the third charge, Q3 we are considering. Q3 means we have to do more amount of work. Already I have told. Why we have to do more amount of work? Because already there are 2 point charges are there, so that the work has to be overcome against the electric field due to the both charges Q1 and Q2, so that here more amount of work must be done. Okay, so what is the amount of work done? It is nothing but Q3 into V, but V is nothing but not only by the charge Q1 but also with the charge Q2, so that I have given the formula, that is nothing but W is equal to Q3 into V1C plus V2C. What is meant by V1C? Electric potential produced by the charge Q1 at the point C. Okay, V2C is nothing but electric potential produced by the charge Q2 at the point C. Okay, right. So that the amount of work done, it is given by Q3 into V1C plus V2C. Okay, right. So the electric potential will be Q3 into, now we can multiply. Q3 will be there, V1C. V1C is nothing but 1 by, what is the value? 1 by 4 pi epsilon naught into Q1 by R13 into Q3. So that I have given here Q1 Q3 divided by R13 plus what is the value of V2C? It's nothing but K into Q2 divided by R23. It is the value of V2. It is given by 1 by 4 pi epsilon naught Q2 by R2. Okay. So if we substitute into Q3, we can write Q2 into Q3 by R3. It is the work done due to the second point charge, work done due to the first point charge. Okay, right. Now, what is the total electrostatic potential energy? We have to add the total electric potential energy, or we have to add the electric potential energy produced by the charge Q1, by the charge Q2, and by the charge Q3. So we are adding all these things. So if we add all these things means, then we can write U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. Okay, so this stored potential energy is equal to the total external work done, because it is due to the first to bring the second charge to the point B. These two is the amount of work done to bring the third charge to the point C. Okay, then one more important point. Since the Coulomb force is conservative, the electrostatic potential energy is independent of the manner which configuration of charges arrived. From which place to which place is not important. Configuration is not up, because if we consider it is placed at the vertices of the triangle, or it is located in some other places in space, whatever it may be, so configuration is not the matter. Okay, so these are the important points we have to remember in the concept of electrostatic potential energy due to the 3 point charges or system of point charges. Okay, are you clear? Right. Now we can move to the next topic. Okay, what is the next? This is also important thing. Electric potential energy of a dipole in a uniform electric field. Already we have discussed about the torque experienced by the electric dipole in a uniform electric field. The same concept, but here we have to understand that from this diagram there are 2 point charges, dissimilar charges, Q1 or plus Q at the point A and minus Q at the point B. What is the dipole distance here? That is nothing but 2A. Okay, then it is aligned at an angle theta with the direction of electric field. Now, if any electric dipole is placed in a uniform electric field, there will be a torque created or generated. Okay, right. Now we can go to the theory part. Now let AB is the dipole placed in a uniform electric field at an angle theta. Because of the electric field, dipole experience a torque. Okay, in the previous video we discussed, if it is a uniform electric field, only the torque will be exerted. Suppose if it is a non-uniform electric field, both the torque and the additional force will be there. Since this is a uniform electric field, only the torque will be exerted. Then in which direction the torque will act? It is a one mark question. It will tends to align the dipole along the direction of electric field. So this electric dipole, it will try to tends to align along this direction. That means this is B, this is the point A. So the electric dipole, it will tends to set the dipole along the direction of electric field. Okay, but to rotate the dipole from the initial angle theta I to theta F, because initially we are assuming that it is at an angle theta, that is considered as theta initial. Now if we are rotate the dipole along this direction, now theta value it may be considered as theta F or theta 2. So to rotate the dipole from the initial point qi to qf, sorry, theta I to theta f. Theta I is nothing but initial angle. This is the orientation of final angle. Okay. Now to rotate the electric dipole from initial angle to final angle, we have to do some amount of work. Okay. Right. This amount of work must be done equal and opposite to the external torque is applied on the dipole, because already torque is there. To overcome the torque, we have to do some amount of work which must be at least equal or greater than that of that, but its direction should be opposite. Okay, so the work done in rotating the dipole from the angle theta initial to theta final in the uniform electric field is given by W is equal to theta I to theta f, because we have to integrate. Actually in our textbook they have left one step. If you want, you can write. Okay, to rotate at an angle d theta, small angle, small amount of work done will be there. That small angle of work done is given by dou into d theta. Then next only W is equal to integral dw. These two steps are left in our textbook. dw is equal to d theta. Then to find the total amount of work done, we have to integrate. Okay, if there is a limit, we will substitute the limit. That is, we have given here. Theta I is the initial angle, theta f is the final angle. So limits are there. So we can substitute W is equal to integral theta I to theta f dou external torque into d theta. Okay, right. Now, what is the amount of torque experienced? That torque, it should be equal and opposite. Okay, then direction should be opposite, but the magnitude of external torque is equal to what is the torque already existing in that dipole. So that we can assume that external torque, modulus of external torque should be equal to the existed torque. Okay, so what is the value of torque? Torque is equal to P sin theta. Okay, so its magnitude, it is equated. The magnitude of external torque is equal with the magnitude of torque exerted. What is the existing torque? So modulus means we will write tau is equal to Pe sin theta. Now we are substituting the value of tau in the equation number 2. What is in the equation number 1. So what is tau? Tau is equal to what? Pe sin theta. Okay, so in this Pe sin theta we are going to integrate. So W is equal to integral theta I to theta f Pe sin theta into d theta. Okay, here we know that what is Pe? It is constant. Electric field is constant. Electric dipole moment, it is P. It is also constant. What is electric dipole moment? Q into 2A. It is also constant. It is kept in the uniform electric field. Kept in the uniform electric field means definitely it will be constant. So Pe cannot be integrated. So that I have taken out Pe in the next step. What will be remaining? Theta, because initially the dipole may be like that, then finally it may be rotated like that or rotated like that. So depending upon the rotation, the theta value will be changed, so that sin theta d theta, the angle of rotation, it will be different, so it can be integrated. What is the integration of sin theta? Integration of sin theta into d theta is equal to minus cos theta. So I wrote that integration of sin theta d theta is equal to minus cos theta with the limit. Already we have discussed about the integration in the 11th standard. So first we have to substitute the final limit, upper limit. Okay, so minus, instead of theta we have to substitute theta f. So minus cos theta. Then next minus, this is minus lower limit. So lower limit means we have to substitute, instead of theta we have to substitute theta I. What is the function already given? Minus cos theta. So that minus of cos theta I, that is the initial angle. Then we know that minus into minus is equal to what? Plus. So in the next step we have written PE into minus cos theta F plus cos theta I. Are you clear? Now W is equal to minus PE into cos theta I minus cos theta F. That is, first we are writing the positive value, cos theta I minus cos theta F. So this is the amount of work done which is equal to the potential energy difference between the angular position. If there are two different angles are there, we will use this formula. W is equal to minus PE into cos theta I minus cos theta F. Okay, right. Then minus PE cos theta I, that is nothing but what? Potential energy only, so that we can write UI. This is UF. Okay, so here we can write U into theta F minus U into theta I. That is nothing but what? Change in or difference in potential energy. So U theta F minus U theta I is equal to change in potential energy, that is equal to del U. Del U is nothing but change in potential energy. So here we can write del U is equal to minus PE cos theta F plus PE cos theta I. That is the previous equation only. We are just multiplying inside. Okay, minus PE cos theta I plus PE cos theta F. Okay, that is given here. Plus PE cos theta F minus PE cos theta F. I. Okay, so this is nothing but change in potential energy or difference of potential energy. Now, in this formula, we can assume that suppose if the initial angle is 90 degree, initial angle is equal to 90 degree, then the dipole, it is considered as it is normally aligned. That is nothing but which is perpendicular. Suppose this is the direction of electric field, means then electric dipole, it is exactly perpendicular. So what is the angle? Theta is equal to 90 degree. So we have considered that the initial angle theta is equal to 90 means then the dipole is normally aligned with the electric field. Then what will be the formula? Okay, so in this formula just we are going to substitute the value of angle. So angle 90 means we will substitute minus PE cos 90 plus PE cos 90, like that we will substitute. Okay, so here initial angle, okay, that is the important point. So initial angle is nothing but theta I. If theta I, if we substitute 90 degree here, means cos 90 is equal to what? 0. So that the complete term, it will be cancelled. Then what will be the remaining? It will be given by del U is equal to minus cos theta F. It is only if and only the dipole is aligned normally with the direction of electric field. Okay, otherwise in general equation the electrostatic potential energy of the dipole in a uniform electric field, it will be given by del U is equal to minus PE cos theta. This is the general equation. This is very, very important. Okay, right. Now we can discuss the special cases of this electrostatic potential energy. Before that, we can see the vector form, because already we have studied U is equal to minus PE cos theta. Okay, in vector form, how can we write it? In vector form, it can be written as U is equal to minus P dot E. Okay, right. Then some important points we have to remember. Now, what are the important notes we have to understand? Okay, so in the first point, electrostatic potential energy of a dipole in an uniform electric field depends on only the orientation of the dipole with respect to the external field. While studying this point, dear students, you have to remember that already we have discussed U is inversely proportional to R, but here we are studying it is only depends on the theta. What is the difference between these two? This is for point charges, this is for dipole. Are you clear? Right. Then the next point we can discuss the potential energy when it will have the maximum value. The potential energy is maximum if the dipole is aligned anti-parallel. So anti-parallel means the theta value is equal to what? 180 degree or pi radian. Okay, right. Now what is the electrostatic potential energy? It is given by minus PE cos theta. Here theta is equal to 180 degree. Cos 180 is equal to what? Minus 1. So we can substitute instead of cos 180 minus 1, then minus PE into minus 1, minus of minus plus, so that the potential energy U is equal to PE maximum, or U maximum is equal to PE. It is also correct. In some guides you may see U max is equal to PE when if it is aligned anti-parallel. Anti-parallel means theta is equal to 180 degree. We can expect one more question from this point also. Then next one is nothing but the potential energy is minimum when dipole is aligned parallel to the field. Parallel means theta is equal to 0 degree. Cos 0 is equal to what? 1. So we can write minus PE cos 0. Cos 0 is equal to 1. So we will write U is equal to minus PE. This is known as minimum electrostatic potential energy. Then the potential energy will be 0 when the dipole is aligned normal with the electric field. Then U is equal to what? 0. Are you clear? So up to this we have discussed 2 5-mark questions. One is electrostatic potential energy of system of point charges, and another one is electrostatic potential energy of the dipole in a uniform electric field. Then nearly 5 or 6 1-mark questions we have discussed from this topic. So dear students, in the homework part you have to write these 2 questions. Question number 1 is electrostatic potential energy due to the system of point charges, and electrostatic potential energy of the dipole in a uniform electric field. Okay, so these are the 2 important topic. Then we can go forward to the Gauss law, electric flux, and also capacitors. Okay, so up to now I think nearly 40 pages we have covered. What are the essential and important points that you have needed for exam point of view, not only for the board exam but also for NEET and IIT? I am explaining clearly as much as possible to my level. So you go through all these contents, and if you find any doubt in this topic you can ask me. I will explain clearly. Okay, so go through all these video till the end, and you have to complete the homework, and it should be posted what you have done earlier. Okay, thank you. Thanks for watching. God bless you.